Hello everybody, my name is John Haley, and for this lesson we shall be covering PV, TS, and TV diagrams. A PV diagram is a pressure volume diagram, a TS diagram is a temperature entropy diagram, and a TV diagram is a temperature volume diagram. Now before we cover these diagrams, we have to understand what is called the state postulate. The state postulate states that for a pure substance you need two independent intrinsic properties to determine any other state properties. Intrinsic properties are properties that do not rely on the material's mass, such as pressure, temperature, specific volume. Now specific volume, if you recall, is defined as meters cubed per kilogram. Go away. Meters cubed per kilogram. As you can see with this unit, it is independent of mass. Same thing if you were to write specific enthalpy, it would be kilojoules per kilogram. Now, independent is very important because you cannot have the two properties depend on one another, and that means if I change the temperature, I change the pressure. Now, I can create a system where if I change the temperature, I do not change the pressure, in which case temperature and pressure would be independent. I can also create a state where I increase the temperature and do not change the volume. Therefore, temperature and volume would be independent. And with ideal material, I can change all of these properties and not change the entropy of the system. Therefore, these four properties would be independent of each other, and which is why we use the different these properties to determine other properties in the system. For example, if I know the pressure of the fluid and the volume, the specific volume of the fluid, I can determine what my temperature is, I can determine what my entropy is, I can determine what my enthalpy is, and various other properties of that fluid at that point. But that will come in a later video in which I talk about the engineering tables. First things I'm going to talk about is the PV diagram, or a pressure volume diagram. In this diagram, temperature is held constant and is drawn using these isothermal lines, as you can see here. They go down, are horizontal during the center of the dome, and head right more. So this is T1. This entire line is one constant temperature. If I were to draw another constant temperature line, it'd be like this, and then back down. This would be T2. Now for the temperature volume diagram, I am on isobaric processes. Isobaric means constant pressure. So if I'm going up here, like this, and then back up, that is P1. Going up here, over, that is P2. These are constant pressure lines. The next is temperature and entropy. These plots also go with constant pressure lines. Constant pressure. Horizontal in the dome, outside P1. In, out, P2. All right, these are the three different diagrams that you will be using in your engineering career. Here. And I shall now get us a new page. Here we go. All right, so now I will label each individual part of the diagram. They will all be the same, have the same points, and same labeling, so I shall be using a PV diagram. That is one of the most common you will use. So if I draw the dome, here's the dome. I'm gonna, this side over here on the far right, not touching the line, this area over here, that's in the dashed. Over here, you are a compressed liquid. A compressed liquid, for example, is pure liquid and you have to pump energy in it for it to evaporate. Now, if you learn the chemistry, you always have to pump in energy for something to change phase or remove energy. But in this case, you have to pump in substantial amounts of energy. Think of it as you have water sitting at room temperature. Water at room temperature would be a compressed liquid. It's just liquid. So, But to increase that to boiling, you then have to pump in a lot of energy, and at that point you're moving up a temperature line. You're increasing the temperature of the fluid. Now this first side here that I will cut in half and circle in green, this part here is called the saturated liquid line. At this point, you're just beginning to start phase changes. This is where you have, if you have, again, the water boiling example we shall use, you just start to see bubbles forming at the bottom of your pot or your container, whatever it is you're boiling the water in. You're just starting to see bubbles forming. At that point, you are now on this saturated liquid line. The next line over here, which I shall circle in blue, is the saturated vapor line. At this point, you are completely vapor, but you just became completely vapor. Like if you boiled everything off and it's all just steam, but it just barely became vapor. And then you're over here in the area I shall once again circle black. This is the superheated region. At this region, you are called the superheated vapor. So remember, this is saturated vapor, and this is saturated liquid. A superheated vapor is where you have, for example, superheated steam. That's steam at where you have to reduce substantial amount of energy for it to come back down to liquid, or just even getting to the saturated vapor point where you can start producing liquid or condensing liquid. Think about it as steam going through your heating pipes. That steam is exceptionally hot and is usually at a couple hundred degrees, and that steam you have to remove a lot of energy to even get back to the saturated vapor point. And the point where both meet up here, that just circled in black, that is what is called the critical point. Often just called CP. At this point, you are both liquid and your vapor. Both phases exist at not just at the same time, but you could go either way in an instant. And so I'll draw the chart again here, and I shall label the states you're at right here. Nope. Technical difficulties. So this is a pressure, volume, dome. Here you are liquid. Here you are vapor. Here you are liquid and vapor. This is inside the dome. This entire structure is called the dome. Inside the dome, you are changing phases. You were liquid and vapor coexist at the exact same time, and depending where you are in this dome, you could be here, you could be here, you have a certain amount of vapor, certain amount of liquid. That will be determined by your quality of your substance, which I shall be covering in the next video. The point of this video is just to get you situated with these type of graphs. Now, I shall do an example process to walk you through every single step, every single part of the diagram. So here, draw another PV diagram. Here's the dome. Here's my process is going to be 1, 2, 2, 2, 3. I'm going to go constant pressure, 2, 4. This is my process. Imagine it is straight. Oh, you know what? I'm going to put 3 here. 4 here, 5 here. So at point 1, you are compressed liquid. Now, different textbooks might call it something else, but the way I learned it is compressed liquid. Here you are completely liquid, and you have to pump in a substantial amount of energy for you to be even come close to starting to boil. Again, an example would be water at room temperature. State 2, saturated liquid. At this point, you've heated the water to boiling, and bubbles are just starting to form. Now this can be any fluid, it doesn't have to be water. I'm just using water because water is one of the most common substances. So we're using water. In here, when you're at state 2, water is just starting to form. You're still completely liquid. Don't get me wrong, completely liquid, but you will start seeing slight phase changes. Point 3, you are inside the dome. Your phase, liquid and vapor, exist at the same time. And this is when you're bubbling and it's really starting to bubble. Like you see bubbles coming up the bottom all the time. This is usually when you start putting whatever you're trying to cook in this water. Number 4. This is called saturated vapor. And at this point, you are vapor. But you just became vapor. So all the water just evaporated right now. If you reduce even a little bit of energy, it can condense. So for example, if that vapor were to, say, reach the cooled lid that you had if you put it on the top, that point you'd be going backwards into the dome. Okay, next is point 5. Get a little bit more room. Point 5. Point 5 is called superheated vapor. At this point, you are vapor and you are very hot. You have to remove a substantial amount of energy to even get back to where you can change phases. So this is superheated steam running through the ducts in a ventilation system, for example. And even though I did all these points for a PV diagram, these also apply for the TV and TS diagrams. The only difference is what property is being held constant, or what properties you're trying to deal with. Here I dealt with PV because that is by far one of the most common properties you will be used. Thank you for your time. In my next video, I shall be covering quality and what it is used for. Goodbye.